Ultrasonic testing. The application of high-frequency vibration to the testing of materials is a widely used and important non-destructive testing method. Ultrasonic waves are generated in a transducer and transmitted through a material which may contain a defect. A portion of the waves will strike any defect present and be reflected or echoed back to a receiving unit, which converts them into a spike or blip on the screen. Ultrasonic inspection has also been used in the measurement of dimensional thickness. One useful application is the inspection of hollow wall casings, where mechanical measurement would be difficult because of part interference. The ultrasonic testing technique is similar to sonar. Sonic energy is transmitted by waves containing alternate, regularly spaced compressions and refractions. Audible human sound is in the 20 to 20,000 Hz range. For non-destructive testing purposes, the vibration range is from 200,000 to 25 million Hz, where 1 Hz equals 1 cycle per second. Magnetic particle testing. Magnetic particle inspection is a non-destructive method of detecting the presence of many types of defects or voids in ferromagnetic metals or alloys. This technique can be used to detect both surface and subsurface defects in any material capable of being magnetized. The first step in magnetic particle testing is to magnetize a part with a high amperage, low voltage electric current. Then, fine steel particles are applied to the surface of the test part. These particles will align themselves with the magnetic field and concentrate at places where magnetic flux lines enter or leave the part. The test part is examined for concentrations of magnetic particles, which indicate that discontinuities are present. There are 3 common methods in which magnetic lines of force can be introduced into a part: longitudinal inside coil, circular magnetization, and circular magnetization using an internal conductor. The selected method will depend upon the configuration of the part and the orientation of the defects of interest. Alternating current, or AC, magnetizes the surface layer and is used to discover surface discontinuities. Direct current, or DC, gives a more uniform field intensity over the entire section and provides greater sensitivity for the location of subsurface defects. There are 2 general categories of magnetic particles, wet or dry, which depend upon the carrying agent used. Liquid penetrant testing. Liquid penetrant inspection is a rapid method for detecting open surface defects in both ferrous and non-ferrous materials. It may be effectively used on non-porous metallic and non-metallic materials. Tests have shown that penetrants can enter material cracks as small as 3,000 angstroms. The size of dye molecules used in fluorescent penetrant inspection are so small that there may be no surface cracks too small for penetration. The factors that contribute to the success of liquid penetrant inspection are the ability of a penetrant to carry a dye into a surface defect and the ability of a developer to contrast that defect by capillary attraction. False posi-UVG results may sometimes confuse an inspector. Irregular surfaces or insufficient penetrant removal may indicate non-existent flaws. Penetrants are not successful in locating internal defects. Eddy current testing. Eddy currents involve the directional flow of electrons under the influence of an electromagnetic field. Non-destructive testing applications require the interaction of eddy currents with a test object. This is achieved by measuring the flow of eddy currents in a material having virtually identical conductivity characteristics as the test piece, comparing the eddy current flow in the test piece, which may have defects, with that of the standard. Eddy currents are permitted to flow in a test object by passing an alternating current through a coil placed near the surface of the test object. Eddy currents will be induced to flow in any part that is an electrical conductor. The induced flow of electrons produces secondary electromagnetic field, which opposes the primary field produced by the probe coil. This resultant field can be interpreted by electronic instrumentation. Defect size and location cannot be read directly during eddy current testing. This test requires a comparative analysis. Part geometry may be a limitation in some test applications and a benefit in others. Eddy current methods can be used to check material thickness, alloy composition, the depth of surface treatments, conductivity, and other properties. Radiography. Many internal characteristics of materials can be photographed and inspected by the radiographic process. Radiography is based on the fact that gamma and X-rays will pass through materials at different levels and rates. Therefore, either X-rays or gamma rays can be directed through a test object onto a photographic film, and the internal characteristics of the part can be reproduced and analyzed. Because of their ability to penetrate materials and disclose subsurface discontinuities, X-rays and gamma rays have been applied to the internal inspection of forgings, castings, welds, etc. for both metallic and non-metallic products. For proper X-ray examination, adequate standards must be established for evaluating the results. A radiograph can show voids, porosity, inclusions, and cracks if they lie in the proper plane and are sufficiently large. However, radiographic defect images are meaningless unless standards are used. A standard acceptable for one application may be inadequate for another. Neutron radiograph. Neutron radiography is a fairly recent radiographic technique that has useful and unique applications. A neutron is a small atomic particle that can be produced when a material, such as beryllium, is bombarded by alpha particles. Neutrons are uncharged and move through materials unaffected by density. When X-rays pass through an object, they interact with electrons. Therefore, a material with a high electron density, such as lead, is nearly impenetrable. N-rays, on the other hand, are scattered or absorbed by particles in the atomic nuclei rather than by electrons. A metal that is opaque to X-rays is nearly transparent to N-rays. However, materials rich in hydrogen or boron, such as leather, rubber, plastics, and many fluids, are opaque to N-rays. The methods used to perform neutron radiography are fairly simple. The object is placed in a neutron beam in front of an image detector. Related techniques. There have been new developments in the radiographic field of non-destructive testing. Several common recent applications include fluoroscopy, gamma radiography, televised X-ray or TVX, microwave testing, and holographic inspection. Force measurement techniques. A brief description of common force measurement tests is listed below. Tensile test. Tensile strength is the ability of a metal to withstand a pulling apart by tension stress. The tensile test is performed by applying a uniaxial load to a test bar and gradually increasing the load until it breaks. The load is then measured against the elongation using an extensometer. The tensile data may be analyzed using a stress-strain curve. Shear test. Shear strength is the ability to resist a sliding pass type of action when parallel but slightly off-axis forces are applied. Shear can be applied in either tension or compression. Compression test. Compression is the result of forces pushing towards each other. The compression test is run much like the tensile test. The specimen is placed in a testing machine, a load is applied, and the deformation is recorded. A compressive stress-strain curve can be drawn from the data. Titration. A titration is a method of analysis that allows determination of the precise endpoint of a reaction, and therefore the precise quantity of reactant in the titration flask. A burette is used to deliver the second reactant to the flask, and an indicator or pH meter is used to detect the endpoint of the reaction. Titrations are used in chemical analysis to determine the quantity of a specific chemical. Hardness measurement. Hardness testing, which measures the resistance of any material against penetration, is performed by creating an indentation on the surface of a material with a hard ball, a diamond pyramid, or cone, and then measuring the depth of penetration. Hardness testing is often categorized as a non-destructive test, since the indentation is small and may not affect the future usefulness of the material. Listed in the next slides are the most commonly used techniques for hardness measurements. Rockwell hardness testing. The most popular and widely used of all the hardness testers is the Rockwell tester. This type of tester uses two loads to perform the actual hardness test. Rockwell machines may be manual or automatic. The Rockwell hardness value is based on the depth of penetration, with the value automatically calculated and directly read off the machine scale. This eliminates any potential human error. At least 3 readings should be taken, and the hardness value averaged. There are approximately 30 different Rockwell hardness scales, with the most common being the HRB and the HRC when used in testing materials. Rockwell superficial hardness testing. The superficial hardness tester is used to test hard, thin materials. It tests closer to the surface and can measure case-hardened surfaces. The testing procedures are identical to regular Rockwell testing. There are approximately 15 different superficial Rockwell hardness scales. Brinell hardness testing. The Brinell hardness testing method is primarily used for bulk hardness of heavy sections of softer steels and metals. Compared to other hardness tests, the imprint left by the Brinell test is relatively large. This type of deformation is more conducive to testing porous materials, such as castings and forgings. Thin samples cannot be tested using this method. Since a large force would be required to make a measurable dent on a very hard surface, the Brinell method is generally restricted to softer metals. The HBW, or tungsten carbide ball, and HBS, or steel ball, have replaced the prior BHN, or Brinell hardness number scale. Vickers hardness testing. Vickers hardness testing uses a square-based pyramid with loads of 1 to 120 kilos. The surface should be as smooth, flat, and clean as possible. The test piece should be placed horizontally on the anvil before testing. The angle of the diamond penetrator should be approximately 136 degrees. Vickers hardness is also done as a micro-hardness test, with loads in the range of 25 grams to 1 kilogram. The Vickers micro-hardness test is similar to the Knoop micro-hardness test and is done on flat, polished surfaces. The units are HV and were previously DPH, that is, diamond pyramidal hardness. Mohs hardness testing. In 1824, an Austrian mineralogist by the name of F. Mohs chose 10 minerals of varying hardness and developed a comparison scale. This scratch test was probably the first hardness testing method developed. It is very crude and fast, and is based on the hardness of 10 minerals. The softest minerals on the Mohs scale is talc, and the hardest is diamond. File hardness testing. File hardness is a version of the scratch testing method, where a metal sample is scraped with a 1/4 inch diameter double-cut round file. If the file whites into the material is not file hard. If there is no mark, the material is file hard. This is a very easy way for inspectors to determine if the material has been hardness treated. Sonadur hardness testing method. The sonadur is one of the newer test methods and uses the natural resonant frequency of metal as a basis of measurement. Hardness of a material affects this frequency and therefore can be measured. This measure is considered to be very accurate. Shore scleroscope hardness testing. The Shore scleroscope is a dynamic hardness test that uses a material's absorption factor and measures the elastic resistance to penetration. It is unlike the other test methods in that there is no penetration. In the test, a hammer is dropped and the bounce is determined to be directly proportional to the hardness of the material. The Shore method has a negligible indentation on the sample surface. A variety of materials, shapes, and sizes can be tested, and the equipment is very portable. Torque measurement. Torque measurement is required when the product is held together by nuts and bolts. The wrong torque can result in the assembly failing due to a number of problems. Parts may not be assembled securely enough for the unit to function properly, or threads may be stripped because the torque was too high, causing the unit to fail. Torque is described as a force-producing rotation about an axis. The formula for torque is torque equals force times distance. Torque is measured by a torque wrench. There are many types of torque wrenches. However, the two types most commonly used are the flexible beam type and the rigid frame type. Torque wrenches may be preset to the desired torque. The wrench will either make a distinct clicking sound or slip when the desired torque is achieved. Torque measurement, impact test, and steel rule. Impact test. Impact strength is a material's ability to withstand shock. Tests such as Charpy and Izod use notch samples which are struck with a blow from a calibrated pendulum. The major difference between the two are the way the bar is anchored and the speed in which the pendulum strikes the bar. The steel rule. The steel rule is a widely used factory measuring tool for direct length measurement. Steel rules and tapes are available in different degrees of accuracy and are typically graduated on both edges. Summary: process capability. In this section, you learned about the following: how to perform capability analysis. What is the concept of stability? What is attribute and discrete capability? Which are the different monitoring techniques? Summary: measure phase. In the define phase, you learned about what are the different process definitions? What are Six Sigma statistics? How do we perform measurement system analysis? How do we calculate process capability?